Okay, right. So we are on air, I hope. And let me just open up questions and answers and do a screen share with my desktop. Okay, start screen share, that's how it usually looks. And this window needs to be a little bigger. And this window, I still can't make it smaller. I don't know. But never mind, we'll survive. So there we go. We're on air. I'm going to set my timer to prove to everybody at home. Why is it so gritty? I think it wants a little careful. I think it wants a little light. Oh, that's a lot of light. But never mind. Here I'm setting my timer to 10 minutes. It's ticking. Yes, it is. So when that goes off, I'll check the questions and answers. So guys, I'm a little disappointed because I was expecting at least 200, 300 students, but you're going fewer by the minute. I can only hope that all the students are not here, Brian, are working on the project. Are you working on your project? You done? Hand it in? Are you going to hand it soon? When? Before 2 o'clock? Okay, because 10 to 2 is the cutoff. After that, you won't be able to hand in. You remember that, don't you? Yeah, and you all remember that. So 10 to 2, you have to stop because the system is not going to allow you. If you do not hand in, I'm not going to give you marks. You will have 0 for your project. Somebody asked me about the minimum mark you have to have for the project. And I thought, oh, well, this is not too important. But then I had a little lookie on our website. And I was quite naughty. I just copied this information from last year without really deciding if I really wanted it. But apparently, it says a sub-minimum of 40% is set for the practical project. So for both the projects, you need to have 40% to pass the entire course. Otherwise, you have an incomplete. I'll have to kick you out. As well as the average of the 2 semester tests. You need an average of 40% for the semester tests. Otherwise, you have it incomplete. Okay. So I think that's fine. I'm a little confused because I haven't taught first years in a long time. I've just been teaching other courses, and I forgot how much mental stress is involved, emotional stress. And Tuesdays is my research day, and I try to devote it to research. But I spent the whole of yesterday answering emails about the project, and particularly from ill people who have discovered the medical certificate and have to rewrite. Now, I mean, if you're really feeling bad, then I don't want to add to your misery by being nasty to you, but you do create a lot of trouble. You do create a lot of trouble, so try not to fall ill during term time. Try to time your illnesses for the holidays. Okay? Plus, if you are ill, don't feel bad about it. Come and tell me, and I have a soft heart. We make arrangements, but there's only so much we can do. So you can't write the makeup test if you are not ill but just had a bad mark. You can't ask to take the test again. If you have one opportunity, and the second test is only for people who have some medical condition and a medical certificate to prove it. And the same for the project. Gee, I feel bad for you if you are ill on the project, but if you are ill, then I've scheduled the second opportunity to demo your project on the Monday of next term. And if you can't make that Monday, that's just too bad, but you'll have 0. Okay. Ugly donkey. That's nasty stuff. Let's not talk about that. Let's talk about our favorite topic, which is insertion sorting. So I just want to make sure that I explain this properly because it's such an exciting thing. Just want to double check if I'm on air and I'm live and I've got Q&A here, and so I'm just going to assume everybody's happy. I just want to take another whack at quickly showing you insertion sort because it's a beautiful algorithm. It is actually one of the best algorithms available, amazingly. I'm just going to find my numbers. I'll do that. And I'll show you one or two special cases. No, I want something blue. Okay, right. Okay, let's just get out of the glare, right? In fact, I think I can do this. Oh, that's beautiful. You can even see my hands. Okay. So what's the idea of insertion sort? We're going to sort the algorithm from the front. So we're first going to sort the one element array, and we don't really have to do that because it's always sorted. An array with just one element must be sorted. Okay. Then we're going to sort the two-element array, which at the moment is not sorted. And then we're going to sort the three-element array, which is not sorted at the moment, but we'll sort that. And then we do a four-element array, and then we're done. And how do I sort, let's say, the two-element array? Well, the prefix, everything except for the last element should be sorted already, and we know it is. Just the 6 on its own is sorted. But now I have to add the 5. And how I'm going to do that is by now working from the back and putting the 5 in its correct place. So I'm going to kind of take it out of here. I'm going to keep it in a special variable. Well, actually, the code that we have works a little differently. What it says is start here at this element, which it calls J. We'll see in a second. And look at the previous element. And if 5 is smaller than 6, swap. So do an exchange. And now we have to stop because 5 has reached the front. It can't go any further. And we can stop. This array is now sorted. I've inserted the 5 into this array into its right position. And now my two-element array is sorted, and I'm going to attempt the three-element array. I'm going to start at the 1 and insert it. Is 1 less than 6? Yes, swap. Move down. Is 1 less than 5? Yes, so swap. Move down. Can't go any further because 1 has reached the front. So I can stop, and my whole array has been sorted. Okay, last step, I'm going to sort the 4-element array. First 3 are already sorted. All I need to do is insert the 5. So start at the 4, sorry, insert the 4. So start at the 4, less than the previous one, yes, so swap. Less than the previous one, yes, so swap. Less than the previous one, no, so stop. It's either swap or stop. Or I've reached the start. So that's how insertion sort works, and how it's sorted. Just to make sure we understand this 100%, let's have a little thought experiment. What sequence of numbers will cause me to make the most swaps? Well, let's see. Doesn't really matter what I put first, so let's start with 6. If I put 5, then 5 has to go right to the front, so it has to insert it all the way down to the front. So that'll definitely cause the most swaps just for one element. And the same is true for the next one. If it has to be swapped right to the front, that'll cause the most swaps. That's the most swaps I can do for one insertion. So I'm going to choose the one that needs to go right to the front. And then I'm going to choose the one that needs to go right to the front. So if it's in descending order and I want to sort it in ascending order, then that'll cause the most swaps. Now, at this stage, I said, I need the one that goes right to the front. And I could have put the 1 there. That would also... questions? Oh, man! You fast with the questions. I'll get to the questions in a second. Now I'm neglecting the questions. I'm making you guilty. I could have put the 1 there, and that would also have needed to go right to the front. But if I next put the 4, that would actually mean fewer swaps because it now only has to go to the second position. So by putting the 4 first and the 1 last, I'm guaranteed that the 4 needs to go right to the front, and that the next one, the 1, also needs to go right to the front. So for insertion sorting, a descending, it's already sorted, but in the wrong order, descending order. Descending is the worst. What is the best order? Fewer swaps. What does that sign mean? Somebody in the audience made that sign. What does it mean?
Ascending.
Ascending, right. Already sorted in ascending. 1 is already fine, we don't have to bother with that. If I put the 4, I make 0 swaps. And if the 5 comes next, I make 0 swaps. And if the 6 comes next, I make 0 swaps. So ascending sort is actually very fast for arrays that are already sorted, but we don't know they're sorted, and almost sorted. Even if it's almost sorted, if I just change those around, this is an almost sorted array. Most are in the right position. Just a few are not. Well, 1 pair. But in this case, I only have to do 1 swap. Or, for example, if it was like that, it's almost sorted, only the 4 and 5 are the wrong way around, then I would no swap, oh, I need to swap this, no swap. So 1 swap to sort this whole array. Just before I get to the questions, let's just count. How many swaps do I need to make? 0 for the 6, 1 for the 5, 2 for the 4, 3 for the 1, and if I had more elements, 4, 5, 6, 7, 8. So it's 1 plus 2 plus 3 plus 4 plus 5, up to n minus 1. And that's quadratic. The quadratic number of swaps, quadratic in the number of elements. We'll get to that again soon. And in this case, how many swaps do I have to make? Well, 0. So that's. Let's just go through the questions quickly. I guess they're in the other order. Select those questions. Oh, you answered twice. Good, excellent. I'll only answer it once. What are global variables, and what is considered abuse of them? Oh, this is a serious topic. We're now going to talk about abuse. Okay. Are instance fields global variables? Good question. Are private and protected variables in the main framework class global variables? So, a global variable. Well, in the old days, when we wrote without object orientation, we didn't have classes. We only had these, let's call it, we did have modules, but they weren't classes, and it's really very different. But even in those modules, and in our classes now, there is something called a global variable. We make a distinction between global variables and local variables. And that distinction is very easy. A local variable is something that's limited to a method, or even to something inside a method like a for loop. If we just look at this slide, J, this variable J that we declared here, we only declare it for the for loop. So outside this for loop, so except for this code, J does not exist. We can't talk about J. It doesn't exist. It's local only to the for loop. And I is local only to this piece of code. It's only local to this for loop and everything it contains. So only those things inside this for loop can see I. It would be wrong to talk about I on this line or even after the for loop. It doesn't exist. It's local only to the for loop. N is local only to method sort, which is why we can't talk about N in this method exchange or ex. N belongs only to this method, so it's local. It's basically limited in scope. Scope is the areas of the code where you can see a certain variable. Okay, let's try something more advanced. A, is that a local variable? Well, not really. It's limited in scope, and we can only see A inside sort. I know we're talking about A down here, but this A, we can really only see inside sort. So it's local to sort, but we don't usually call it a local variable. Parameters, arguments for methods, are like local variables, so they're limiting their scope. But we don't usually call them that, although it would not be entirely wrong if you did. Let's just go to exchange. So I said A is local to sort, so why are we still using it here in exchange? Well, this is a different variable, and it's also called A, but it's not the same A. It's just two A's of the same name. I'm sure you're familiar with this concept. I'm sure you have two friends with the same name. You know they're not the same friend. Okay? Their name is local to that one person. Right. And we can prove that by being able to change A to B. And nothing would break. If we just change this A everywhere we use it to B, nothing would break in this code. That's somehow a little test of the fact that it's local. And there's also I that's local only to exchange, and a J that's local only to exchange. And swap is local only to exchange method. So this particular code doesn't have any variables, global variables. But if we were to have a variable up here inside the class, but having it what we call an instance field. It's not an instance method. It's not inside an instance method. It's a field of the class. Every time I create an instance, that instance belongs to, that instance has a copy of that field. So that is what we would call in this context a global variable. It's global because everybody can see it. All the methods can talk about that field. If they're public, they can talk about it, but even if they're private methods, they can still access that field that I declared in the class. Let's see if I can find a little piece of code with a jumping ahead. No, that's inside a method. Okay, I can't find one immediately, but I hope you understand what I'm saying. Is a variable global if it's static? Zeg weer een naam. Johannes. Marco. Okay. Wie zit langs je, Marco? Wie? Deep penetration. Oh. It's a kind of ointment that you put on muscle. DP. Okay. DP. What does DP stand for? Pierre. Diderot, Pierre. No, not Diderot. Daniel, Pierre. Denouement, Pierre. Parlez-vous français? Zut alors. Parlez-vous quelque français? Rien, pas du tout. Let's stick to English then. DP, or whatever your real name may be, you're falling asleep a little bit. I can see that. So I'm going to wake you up by asking you intense questions. Static fields, are they global? Well, it's a little test you have to do. Can all the methods see them? Yes, so they're global. What about final fields? Are they global? Can all the methods see them in the class? I can't give you hints, so I can't shake my head because the internet may notice. But I want to. No, everybody can see them. All the methods in that class can see them, of course. So they are global for the class. Now, whether they're final or static doesn't really matter. They're global in their class, the instance fields, but they may not be visible outside the class. If we make them public, they will be visible to everybody, all the classes in our program. If we make them protected, they're only visible to us and to our children, our subclasses. So that's kind of global. It's not all the way. So other funny classes can't see them, but my children can still see them. And if they are private, even my children can't see them, but they're still global to all the methods in this class. So all the methods in this class will share. If int n was declared outside here, just after this class, this brace, then all these methods, sort and exchange, would be able to see n and to talk about n. Even if it was private, even if it was static, even if it was final, that all CN. Now, just one last thing. I'm talking a lot about global variables, but they're really important. You want to limit the global variables as much as possible, because global variables are bad. They're bad because I'm routine sort, and I'm using a global variable to store something, and I think I know what's going on. Then I call a different routine, a different method, and they actually change that global variable. Without my knowledge, they change it. And when that method terminates and I come back in control, I get control back, the global variable has changed, and it's not what I think it is anymore. If that method wanted to return a value to me, it could have used a return statement. If it instead put its result in a global variable, that's a bad way to pass information from one method to another. So we want to eliminate as many global variables as possible. Sometimes it's not possible. I mean, in some sense, object orientation is about this kind of containment. You have a few global variables that represent the state of an object. Then we have all these operations that can change the state. So we do want different methods to be able to change the global variables. But we also have to be careful because they're a potential source of errors. The fewer global variables we can store, the better. We try to eliminate global variables. Now, Ich was actually speaking specifically about the main/framework variables. There are a few global variables because different methods change them or update them, create them. They're supposed to be private, but I can't recall the source code exactly. Perhaps they're public, but they shouldn't be public. They should try to be as private as possible. We want to encapsulate. We want to limit access to our fields, our global variables basically, and to our methods. We only want to expose as few methods as possible so that we remain as independent as possible from the other classes. So that later on we can change the class, this class, and how it works. So they may be public, but they should really be private, and you must always try to make as many of your methods and fields private as possible. So I'm going to say that's done, and then I'm going to also mark this question as done because it just asked it twice, probably a little slip. Can you do insertion sort? Finally, back to my real topic. By doing so and send the elements to the end of the array. Insertion sort in reverse. Can we do it from the back? Someone says, of course you can. And now I'll show you why it won't work. No, it won't. Of course it will work. It's not more difficult. It's just more traditional to do it from the front. I don't know why. You must always see insertion sort from the front. So, but you can do it from the back. There's nothing wrong with it. It's just a mirror image. In fact, we'll think about it. We'll talk about it in a second. But if you do it from the back, I start with a one-element array that's already, which is jumbled. I start with a one-element array that's already sorted. Now I move on to my two-element array. And I'm going to start at the front and swap towards the back. Is the next element smaller than 1? No, the 5 is not, so it stays. And I can stop. There we go. Next element. Start from the front. Is the 6 bigger than the 1? Yes, I have to swap. Is the 6 bigger than the 5? Yes, I have to swap. I've reached the end, I have to stop. Now we do the 4-element array. Start from the front. Is 4 bigger than 1? Yes, I have to swap. Is 4 bigger than 5? No, it's not. I have to stop. So there is the array sorted in ascending order, and I did it from the back. And I wonder if I should keep this question for the final exam. Brian, what do you think?
I'll stand you for that one.
Say again?
What I'm saying is, how would you then, like, this is all for ascending order. How would you interpret it for descending?
In descending order, it doesn't really matter to us because we have this wonderful compare to that compares the elements, and it sends back the result -1, 0, +1. And if we want descending order, all we do is change the bigger than to the smaller than. That's descending order. Yes, let's see. Oh, and no, Baveen and Jason. Scott. No, you're not Scott. Peter. No, that's Scott. What's your name?
Matt.
Matt. Oh, of course, Matt. Yes, Matt.
Could you?
We were just talking about you in the department. Yes.
Could you do insertion sort from both sides simultaneously to speed up the process?
Oh, so you want to start there? Well, hang on. Like so. With two arrows.
No, you go. I don't know if you have two arrows.
This. I mean, I can write at least 20 questions on insertion sort. Let's try Matt's brilliant idea. What Matt is saying is that, look, there's this whole big array, and every time I have to potentially swap right to the front. So what if I halve my work and I start from the ends? They're definitely sorted. A one element array is always sorted. This one element array is always sorted. So I'm going to start from the back, and then each time I'm going to take this element and sort this part, and take this element and sort this part.
Yeah.
Is that right, Matt?
Yeah.
Is that what you want? Is what you really, really want? Okay.
I really want that.
Okay, let's start. Okay, right, here we go. Matt's sort. We'll call it Matt's sort. I don't want to besmirch the name of insertion sort with this little operation. I just need to move this a little further apart. Okay, start with the two ends of the array, and individually they're still both sorted. And I'm going to take turns. The left array, the right array, left array, right array. And for the left array, I'm going to start by inserting the 4. So start at the end. I'm doing the normal insertion. Math is 4 less than 6.
Yeah.
Yes, I definitely need to change that. So I've sorted the left part of my array. Now it's the turn of this part. I'm now doing insertion sort in reverse, as we just learned about. Math is 1 smaller than 5, so I'm going to stop. And now there are no more elements to insert. I've reached the empty middle, and I'm done. Ta-da! Help! Math, help! The thing isn't sorted. We should probably check if 1 is less than 4, then the parts are just in the wrong sides. So I just need to swap them. There we go. Happy, Matt? Now I'm going to reveal that this all along was Matt's pin code. What's wrong, Matt?
5 and 4 in the wrong order.
Damn. How are you going to fix that?
By running this again.
The whole thing?
I know that's not good.
No. Forever the 5 will be in the one part and the 4 will be in the other part. And even if I change them the right side around, the 6 is with the 4, so now it's in the wrong part, and the 1 is with the 5, so now that's in the wrong part. Nothing I can do to fix this. But we're going to return to your idea in just a sec, I promise. So brilliant idea, and I'll save the question that Brian wanted for the test. Okie dokie, so this has been done. Thank you, Shane, for the beautiful question. You've made us all very happy. Okay, right, so this is sorting, and this is the exchange routine that I'm using to swap these elements. Exchange is extremely common. We use it all the time in sorting algorithms, because sorting is often the idea of I have I'm looking through my array, and I find 2 that are in the wrong order, and then I have to exchange them. So exchange happens quite a lot in these sorting algorithms. So now they're talking about an empirical analysis. How long does the sorting take? And we've already talked about that a little bit. This is tricky. Bottom line is that this is a log scale. So we must remember that polynomials are going to show up as straight lines. And here we can, in fact, see one. In fact, even the constant is showing up as a linear function is showing up as a straight line. So this graph isn't really very interesting to me. I don't think there's an more interesting one either. But this is what we're really interested in. If we are going to, if the array is already in descending order, if the array is in descending order, and so exactly the order we don't want, we will need to do every single possible swap, because each element we have to insert right to the front. So that's going to take n squared over 2, roughly, insertions or comparisons or swaps. If it's just any random order, we can kind of bargain on n squared over 4. And I don't think it's necessary for you to be able to derive that, but you should definitely know that in the worst case, when the arrow is unsorted or sorted in the wrong way, this will take n squared over 2 comparisons. But if it's ascending, we only have to do n comparisons. Every time we add one element to the n, we only compare it once. Let's just see that again. If it's already sorted, we start here, we try to insert the 4, compare it to the 1, that's one insertion, but it's the right order, so we can carry on. Try to insert the 5, compare it to the 4, that's the second comparison, but it's in the right order, we don't have to swap. Compare the 6 to the 5, right order. So we still have to do some comparisons, n minus 1 of them, but it's much less work than when the arrow is sorted the wrong way. Why do they say n here when I just said n minus 1? Well, if you remember, this tilde notation means roughly. So we throw away all constants, basically. Okay, I know we still have a constant there, and it's not that easy. But what we have is, after tilde, we expect some kind of polynomial, and then we just take the highest term, the most important term. So this used to be n minus 1. The minus 1 is not important. It's a lower order term, so we throw that away. This n squared over 2 is actually the whole polynomial. So that's a little empirical analysis, and this actually explains it. So if it's in the worst case, it's descending, so already sorted but the wrong way. We do 0 swaps to insert the first element, but we have to, because one element array is always sorted. But we have to do 1 swap when we insert the second element, and 2 swaps when we insert the third element, up to n minus 1 swaps for the last element. And if we add that up, we did this before, it's on the class notes, we get n squared over 2. Plus n plus something, but we throw away the low order terms because we're using this tilde notation. It's only the highest order term that's really important for us. Okay, so I said you don't need to know, but it is interesting to see how they arrive at the average case. So in the average case, what we're saying is that in the best case, each insertion requires 1 comparison. In the worst case, each insertion requires n minus 1 comparison. In the very worst case. But on average, we can expect about half to compare to with half the elements that are already there. So it's almost the same as this formula, except we don't do as many comparisons. For each of those insertions, we only do half, which is why we divide by that sum, we divide that by 2. Half for the first insertion, half for the second, half for the third. And that's why we end up with n squared over 4 comparisons at the end. So this formula and that formula is exactly the same, except I've halved the number of insertions I have to do, and so it's over 4 and not over 2. Okay. Let's see. Simone, whatever your name is. A credit card company sorts 10 million customer account numbers with insertion sort. What kind of computer do they need? Well, what answer the question, Simone?
I think it's not going to be a laptop.
You are wrong. Want to change your answer? You want to phone a friend?
Sure.
Usually on You're a Millionaire, you want to be a millionaire. Do you know that show? You want to be a millionaire? Do you know that show? It's a quiz show. Do you know it?
Yes.
Okay, yeah. Usually, when you answer wrong, you lose all your money. You're thrown out. Boop, boop, indeed. But here you have another chance. So C is not correct. Do you want to change your answer?
I'm just going to ask, what is the time constraint?
You're not allowed to ask questions in the quiz.
Yeah, It's just going to take really long.
You could do it with a what?
Any chip.
Any chip. But any chip is not on the list. Pick a chip. Pick a toaster. Because you can do it with a toaster. If there are no time constraints, then who cares? I don't care if it takes long to solve credit card numbers. But let's see, if we do want a time constraint. Let's say, what kind of time constraint is reasonable? Is it okay if it takes a year? Probably not, because that's quite long for a credit card company. Is it okay if it takes a month? Oh. Now, why do they want to sort these customer account numbers? They want to use binary search. But they only have to do it once. I mean, it's not something they have to do every single day. So if it takes a month, then that's okay. Although if they get any new customers in that month, they'll can't be added. So probably a month is too long. What about a week? I think credit card companies get customers every week, new customers. You want them in the list, don't you? So a week is probably too long also, but a day is fine. I mean, if they only add their new customers at the end of each day, and then overnight they sort the list so that the next day they can look up customers quickly using binary search, then that's fine. So a day is okay. I still think, though, a toaster will take more than a day to do that. I think your cell phone might also take a long time. Your laptop could probably easily do 10 million customer account numbers in a day. I'm guessing. I'm sure. I'm almost sure. So laptop, Simona, is the right answer, I'd say. But you didn't say it the right way. You didn't say what Ryan said. What's the time constraint? Because that's the important part of the question. Ugly duckly. Oh no! Oh no! Amazing. I was so wrong. How many do they have? 10 million customer accounts. So this little slide says that if you can do 10 to the 7 comparisons every second, and you want to sort 1 million records, that'll take 1 day. So 10 million records will take 10 days. That's too long for our company. If we had a supercomputer, it would take 10 seconds. But if we had 1 billion customers, it will take 2 weeks with a supercomputer. But my question is, do we have a credit card company with 1 billion customers? It's 1/7 of the Earth's population. I doubt it. I don't think so. So this 2 weeks is probably never going to happen. Just 1 second, Josh. Oh, do you want to tell me about the egg timer?
No, I just wanted to think of the people who are home.
I do want to think of them. I know they have questions. I can. Disappointing. Okay. So I'm guessing a supercomputer would probably be okay for our credit card company. Plus, they shouldn't be using insertion sort. They should be using something else. What should they be using? Wow, let's talk about Moore's law. What's Moore's law? It's a very specific thing. It says that the number of little gates, little transistors that they can fit on a silicon chip, I guess, a computer chip, integrated circuit, doubles. The number doubles every 18 months. So every 18 months, they can fit twice as many little transistors on a silicon chip as they could before. And roughly the number of transistors corresponds with the speed. So we can roughly say that the speed of computers doubles every 18 months. Now, this isn't based on theory. This is based on empirical observation. What Moore did was to plot the different speeds of computer, actually the different number of transistors that they fit on chips since the 1900s. And here he had to estimate because the transistor wasn't really invented until here-ish. There we go. So, but before that, they used things that are equivalent to transistors. So he plotted this on a curve. This is exponential or log scale. And he found this trend. And that's why he postulated the Moore's law, that this is how speed doubles. And it's been very, very accurate. It's been extremely accurate until a few years ago. And today it's not in operation anymore. It doesn't work. It's not there. It still applies to some components, perhaps like memory or storage, but it doesn't apply to computer chips. And the reason is that if you fit more and more components on the same area, on the same chip, then each component has to become smaller and smaller and smaller. And we've now reached the limit because they can't be smaller than one atom. If it's less than one atom, we're dealing with, I guess you could still deal with subatomic particles, yes. But we don't have that technology. So we're at a stage where we just can't go any further because the components are too small physically to make any smaller. So it has stopped working in some sense. But now they try to compensate for that by putting many chips inside each computer, multi-core machines, trying to distribute work not over one computer but over many, so that I could have, as I do when I do my own research, I have a server with 32 different computers inside, and each of them has several cores. So I have, let's say, 64 cores working on my problems. So we tried to do that kind of improvements, but Moore's law is essentially run out. And this is kind of important because it solves, or it talks about a very specific puzzle or riddle that we've had. Every 18 months, our computers roughly double in speed. So they become, let's say they become 10 times faster than 4 years ago. So my computer is 10 times faster, but when I work on it, it still feels to be the same speed. But it feels even slower than the computer I had in high school. So how's that possible? Why isn't the experience of the user speeding up tremendously as the computers grow faster? And the reason is that as the computers grow faster and the memory grows larger, I want to tackle more and more complicated problems. My computer is 10 times faster and can store 10 times more data, but now I want to store that 10 times more data. I had a primitive graphical interface, but now I've got a really complicated graphical interface. I had very simplistic level games, shoot 'em ups, when I was in high school, but now I want super realistic 3D, Oculus Rift, stereo vision, full sound over the internet multiplayer games. So that the things I'm trying to do is much more complicated. So the computers have speeded up. The task I'm asking of the computer has speeded up, but the algorithms are basically the same. Insertion sort is still n squared, the same as it was 10 years ago. We haven't speeded up insertion sort. We do have faster sorting algorithms, but they don't speed up either. They stay the same. And in fact, we know what the very fastest sorting algorithm is that can exist, and we have algorithms that are that fast. But they stay the same speed. So if my n is 10 times bigger, then I need to do n squared as many comparisons. So let's see, n is 10 times bigger, so I have to do 100 times more comparisons. Never mind that my computer is 10 times faster as well, it's going to feel 10 times slower. The computer is 10 times faster, but I'm asking it to do 100 times more work. So it's going to feel 10 times slower. So that's a sad tragedy of Moore's law. What does this guy say? Why does he have dreadlocks? Doesn't look Jamaican. Software inefficiency can always outpace Moore's law. Well, that's true. If you write bad programs, if you write inefficient software, that's no match for any computer. No computer is a match for that. If you write bad software, it will always be bad. It doesn't matter if you double the capacity of the computer. You can't fix bad software by just saying, let's buy a better computer, a faster computer, or one with more memory. Sometimes that's a short-term solution, and companies do that. And you'd be surprised how many companies do that. A company is in trouble, they need to deliver a product to a client next week. It's running too slow. What's the solution? Let's buy a brand new computer, we'll just run it faster. Anyways, back to Jaron Lanier. Is that a real person, or is he from science fiction? Wasn't there a Lanier on that Babylon 5 space? I'll check in a second. Software inefficiency can always outpace Moore's law. Moore's law isn't a match for our bad coding. Yeah, well, speak to yourself, Lanier. I'm not going to do bad coding. I'm going to do good coding. Who this clown is. Oh no! His second name is Zeeple. Oh my god. What is he playing? Oh, well, he looks like okay guy. He's an American writer, computer scientist, and composer of classical music. That's nice. Pioneer in the field of virtual reality. Good. The first company to sell VR, virtual reality goggles and gloves. Oh, that's impressive. Our department has just ordered our first Oculus Rift, and next year we'll be assigning honors projects to do stuff with it. So we don't want people to just write games. We want them to use it for research kind of stuff, helping people to visualize stuff. We haven't decided exactly what they're going to do, but so this guy is a pioneer in that field. That's great. He worked on applications for Internet 2. He was a visiting scholar at Silicon Graphics. Silicon Graphics used to be a computer company that made these great machines that were capable of, I have to stop. I'll just show you the Oculus Rift before I go. Let's just see the Oculus Rift. Oculus Rift. Just to whet your appetites. Oculus Rift. So, it's this device, like goggles, who knows what it is? It's like 20%, 30%. It's this device that you put on, it's like goggles. It has separate little computer monitors for the left and the right eye, so it allows you to see in 3D. This has been around for a really long time. In fact, people used to do it much more elaborately by making a cave, a whole virtual reality cave, which is like a holodeck on Star Trek, if you know that show. It's a big room with screens all over the walls and the floor, and you can imagine if you're in some kind of environment when you go in there. But this Oculus Rift just does that for your eyes. It's seen 3D, things are really 3D, except for the internet, which seems to be 1D. Come on, why is it slow? Okay, let's see if we have questions. No questions, that's excellent. I just hope we're still live. Yes, we are. Good. Oculus Rift. Okay, it's not loading, but have a look yourself. It's a really exciting technology. And I'll see you in the demo tomorrow. Good. Excellent. And I'll just stop the broadcast. Thank you for watching.